So I want to talk about kind of the main uses of matrix multiplication to help you understand why we define it the way we do, and I think it'll help you remember the process as well. Uh, so kind of the broad use of matrix multiplication is to organize a system of linear equations. We'll also talk about regression analysis, which is exactly why we as empirical social scientists need to understand matrix algebra. It's kind of really a subset of the overall topic of linear systems. Okay, so what does that mean? What's an example of a linear system? So I'm going to write down three equations, and I'm going to have three variables here. So 3x1 plus x2 plus 7x3 equals 32. That's the first equation. Second one is x1 minus 5, x2 plus 4, x3, that equals 4. And the final one is negative 2x1 plus 6, x2 minus x3, that should equal 5. Okay, so this is an example of a linear system. Okay. It's a system because it's got more than one equation. It's linear because we have these three variables, x1, x2, and x3, but all we're doing is multiplying them by constants and adding them up. So there's no exponents, there's no multiplying x1 by x2 or taking logs. There's nothing fancy here. If we know the system is linear, then all the information really is coming, what makes one system different from another, all the information that distinguishes it is coming from these coefficients here that I meant to highlight instead, just erased. Here's my 3. So what's the way I've written this system is I've always got my x1s first, my x2s next, and my x3s. I can write it in any order I want. These are just, equations with real numbers, but it's kind of nice to organize them this way. I've put all of my terms with the variables on one side and all of the constant terms, the ones that aren't being multiplied by a variable over here. That's a helpful way to organize these systems. Once we do that, it's kind of natural to put the coefficients all in a matrix. Okay, so check this out. I'm going to take these coefficients and I'm going to put them in a row, and these ones in another row, and these in the third row. Okay, so I'm going to create a matrix here. Let's make my lines a little bit darker. Where the first row is 3, 1, 7. So I've got the coefficient on x1, on x2, and x3 there. From the first equation, the second row in the matrix will be the second equation in the system. So the coefficient x1 there is 1, negative 5 on x2, and 4 on x3. And the final row is the coefficients from the final equation, negative 2, 6, negative 1. Okay. So I've got them all in a matrix there. Well, the other thing that matters for this linear system that might make it different from another one is this vector, or these sets of coefficients here that aren't being multiplied by a variable. They're not a vector yet, but they are going to be right now. I'm going to put them in a vector here. 3, 2, 4, 5. And then let's take my variables and put them also in a vector like this. X2, x3. Okay. So this, the letters that often, not exclusively, but often are used to denote this, we would say this is our A matrix of coefficients, our X vector of unknown variables equals vector D of constants. Okay? And indeed, if you remember how we do matrix multiplication to get the first row, first column of the product, we take the first row of the lead and multiply it by the column of the lag. We get 3x1 plus 1x2 plus 7x3 equals 32. To get the 2, 1 element of the product, okay, this 4, it says that is 1 times x1, there it is, minus 5 times x2, you got it, plus 4 times x3 equals 4, okay? So what we have here is matrix equation that's equivalent to the system of linear equations. And really the field of matrix algebra was created to find the values of X that will make the whole system true, that will satisfy all of the equations, or sometimes to find out that there are no variables that satisfy that. Okay, so that's this example, this taking the set of, in this case, 3 equations with 3 unknowns and turning it into a single matrix equation here is the context in which matrix multiplication was developed. And so it was developed in this way because that's the way to make what we're saying with the matrix equation be exactly the same as what we were saying with the whole set of equations just involving numbers. All right. So for us, what we care about, the linear systems we're most interested in, are our data sets. Okay? So I want to do a somewhat longer example of regression analysis. And so what we do in regression analysis is we have some kind of dependent variable that we think is affected by one or more independent variables, and we collect data on both the independent variable, you know, what happened, and data on the things that we think influenced it, put them in a spreadsheet, rows and columns, and then we try to estimate numbers, betas, coefficients, that represent the impact of each independent variable on a dependent variable. We estimate those from the data. All right, so let's kind of come up with a not super interesting, but manageable example where our dependent variable might be some measure of presidential election outcomes. So we might have the percent of the popular vote to the incumbent party in a presidential election. That's a pretty standard dependent variable if we're analyzing US elections. Independent variable we might be interested in is the country at war or not, okay? And so a variable like this would typically be coded would be 1 would be yes, 0 would be no. The IR folks have various data sets that they use that decide, you know, like how much fighting do you really need to count as a war, or militarized international, I don't know what the last there is. Anyway, you find data on whether people think we were at war in any particular year or not. And that might be a hypothesis, right? So in this little example, that's what we're interested in. Does being at war increase the fraction of the popular vote that goes to the incumbent president's party? There's a kind of a theory saying that there's this rally around the flag effect that would make that effect positive. If we were going to look for that, though, we would certainly want to control for the state of the economy. Okay, so we would have another independent variable. Is the economy doing well? Is it doing poorly? Standard way of measuring that would be probably real GDP growth in the second quarter. Okay. So what we would be thinking of as our regression model here is that for each of our elections, the popular vote, yi, so I'm going to let I index our elections here, is going to be modeled as a constant. I'll say something about that in a minute, plus 1 times x1. Let me write that the other way. Times x1 for that observation, okay, is are we at war or not, plus beta 2 xi2 plus an error term. Okay, so that is what people would call a regression equation. I'm guessing some of you recognize these from work you've done as undergraduates, things you've read before, certainly things that you're going to be reading in your substantive classes this quarter will involve regressions of this form. So the idea is we think that this is kind of a common logic that's applying to all of the elections in our data set. So for this kind of question, we might say, let's have our data set be the election since World War II. That's, again, something that people tend to do when they study American elections. So there's 18 of them. We would have 18 elections. And so I here would take values from 1 to 18. Maybe we could say that it's organized from most recent first. You can do it any way you want, but let's keep that idea that when I equals 1, we're looking at the 2016 election, I equals 2 is 2012, all the way back to when I equals 18, then we're at 1948. Okay, so we've got those 18 rows in our spreadsheet, and each of those rows has an observation for what fraction of the popular vote the incumbent party got, whether we were at war or not, and how GDP was growing in the second quarter. Okay, so each row would correspond to a value of I. Some of the other things that are going on in here, like most regressions, it has what we call a constant term, something that's not being multiplied by an independent variable. And so what you would think beta 0 would represent is the percent popular vote share to the incumbent party when we're not at war, when x1 equals 0, and when x2 equals 0, and GDP is just not growing or shrinking there. So we usually put those in our regressions. We've also got this epsilon term here. That's a Greek letter epsilon, and this is actually a really important part of doing the estimation. This is the part of the dependent variable that we're not explaining with the independent variables in the constant. This is our we call our error term. This is the variables we don't observe, the things we haven't thought of, the totally idiosyncratic things. It might be measurement error in our data. It's all the stuff that is keeping our model from perfectly predicting the dependent variable. Okay, the epsilons aren't going to be super important for this example, but I'm putting them in because they're part of the regression model. All right. So the idea here is, coming back to being a researcher and having this data set, is we have data on the yi's, we have data on the xi1 and xi2, and what we want trying to do is estimate numbers for beta 0, beta 1, and beta 2. Okay, what are the values of these 3 betas that would best explain our data? Okay, so that's how to do that accurately is going to be a big part of PoliSci 200B that you'll take in the winter, and one of the reasons why we're doing matrix applications now. Okay, so continuing to think about, let's take this regression model that we have in our head. The hypothesis here is that beta 1 is greater than 0. Okay, would be the idea that being at war causes people to vote for the incumbent. And okay, so what I want to do is I want to take this equation that's got the I indices in it and write it out for a few observations. Okay, so for 2016, let's say that that's our I equals 1 election. Do it the most recent first. What we would be saying is that YI would be 0.482. That is the percentage of the popular vote that Clinton got. She was the candidate of the incumbent party. And that would equal beta 0 plus beta 1 times, were we at war in 2016? No, we were not. So X1 for the first observation for 2016 would be 0. So that's my beta 1 plus beta 2 times the GDP growth in the second quarter of that year. I looked up, it was growing at 2.1%. 1, okay, plus epsilon 1, okay. So these would be the numbers that we would like have in our data set, in R or in Stata or whatever we're using for our first observation. And then we would have 18 rows. We would have the corresponding number for 2012, 2008, all the way back, all the way down to 1948. I equals 18 for that election. In that year, Truman got 49.6% of the popular vote. Still don't know what beta 0 is or beta 1. Again, it was a year when we were not at war. So that's a 0 on our X1. And GDP growth was 4.6%. 6 plus epsilon 18. Okay. So that data set, with the idea that we've got these unknown betas here, is a linear system, just like we saw in our first example. The thing that's a little bit weird here, and is always weird when you're talking about statistics, is from a theoretical point of view, the X's and Y's are the variables and the beta is the parameter, like some kind of theoretical constant that we're trying to estimate. From the statistical point of view, though, the Y's and X's are the things that we observe. They're like the coefficients. And what the unknown thing we're trying to figure out is the best estimate of our betas here. Okay. What I want to do now is, really have double the amount of space to look at this with. And so what I think I'm going to do is erase the top part. I'm going to clear up some Blackboard space. That's what I do if this was a real Blackboard. So let's see how it works here electronically. Okay. So this is the overall regression model. This is what our system of 18 linear equations in 3 unknowns, beta 0, beta 1, and beta 2. Okay, so these are our unknowns, just like the X1, X2, and X3 in the first example. And so what I want to do now is, just as I did before, take the numbers that come from our data, and put them in matrices. So we have, instead of the 18 versions of the regression model, each with different data values in them, we have a single matrix version of it where the rows correspond to different observations. Okay. So what I'm going to do is I'm going to put my dependent variable, okay, my y values in a vector. Okay. So that will start with the Y value, the dependent variable, the popular vote to the president's party for my first observation, I equals 1, 2016, and I'll have a whole bunch of other numbers here, get all the way down to 0. Sorry, not point. 0.496 there. Truman got 49.6% of the vote, so I'd have all of my Y values here. That's my Y vector. And just as I did before with the coefficients in the boring linear model without a story, here I'm going to pick out my coefficients that are multiplying the constant, beta 1 and beta 2 here. Okay. Well, my beta 0 here is a constant. It's getting multiplied by 1 every time, and regression matrices often start with a column of 1, so I've got my 1s right here. And then for beta 1, what's multiplying that in the first row is a 0, all the way down to a 0 down here. Just noting something here. The 1 really is a 1. We have 18 ones in this column, in the first column. In the second column represents whether or not we're at war. Sometimes it's a 0 and sometimes it's a 1. It's just sort of unfortunate that the beginning and the ending ones, rows both have 0s. But for example, if we were going to look at the 17th row here, corresponding to the 1952 election, we would have had a 1 there because we were in the Korean War at that point. And then we would have the, in the third column of our X matrix, we would have our observations on the second independent variable, those GDP growth terms. So we would have 0, 0 to 1 here, and all the numbers that correspond to GDP growth in election years, all the way down to 1946, where it was 0.46. That's our X matrix. And then we would have a vector of the unknowns we're trying to solve for. In the first linear system, remember, it was x1, x2, x3. Here it is beta 0, beta 1, beta 2. And the final thing would be our vector of random error terms that we would never observe, but we need to be able to think systematically about anyway. Okay. So the matrix equation here is Y equals X beta plus epsilon. Okay. So what I want you to see before I move from this screen that I've been on for a while now, but I want you to see how putting in the different year values for the yi, xi, and x2 into this basic model gave us 18 equations that all had a beta 0, a beta 1, and a beta 2 in it, but had different numbers because every year the values for these variables change. That gave us a system of 18 linear equations where now the data are our coefficients. That's the weird thing. The data are the thing we know here, and we're trying to estimate our parameters. So in this system of 18 equations, the numbers are different in each of the equations, but we always have beta 0, beta 1, and beta 2. And this allowed us to take the numbers from our data and organize them into a vector of n observations on the dependent variable that should equal to the product of an n by k. I'm going to say this whole thing over again right now, so I'm just previewing it. Matrix of observations on independent variables. Okay, so Y vector of observations on the dependent variable is the product of the X matrix of observations on the independent variable times the vector of unknown quantities to be estimated here, our beta vector, plus random error that we know exists, but we can't do anything about. All right, let's write that part here by itself and kind of a relief to write it just in matrices. That's all that's going on. So the regression model in matrix form here is an n×1 vector of observations on the dependent variable. And so it's our n observations on the DV, the thing that we think is being affected by the other things. And so that's one side of the regression equation. Then we have an n/k X matrix multiplying a k/1 beta vector. And then we add to that the n/1 vector of random errors. N, remember, is the number of observations. K is the number of parameters to estimate the number of unknowns here. Okay, so in that case, K was 3 because we're estimating a constant, slope on the whether or not we're at war, and a slope also on the GDP growth here. Looking at it in terms of matrix multiplication, is our conformability all working out? Well, let's start with where it's the biggest issue, right, with multiplication. So we have a column in X for each of our independent variables, plus that constant, that variable that's not varying here. And our beta, so that's K, and our beta vector has indeed the 3 things we're estimating here. So yes, these are the same, but conformability, yay. And when we can do that multiplication, and when we do it, the result is n/1, and that's good because we want to be able to at least think about adding these error terms that, again, we don't observe, but we're trying to think about how they could be affecting our certainty in our estimates here. And that when we add the n/1 product of x beta to the n/1 vector of unknowns, we should get another n/1. So it all works out. Okay, that is a lot of regression model with really very minimal context. Like I said, you're going to have a whole class in regression analysis in the winter. And so don't, especially if you're new to regression analysis, don't feel like you have to wrap your brain around every detail here. But this is where you'll be going with matrix multiplication. What I want you to be comfortable with at this point, and what I think is worth kind of working through yourself, is going back here, the process that got us through kind of a logical story about the effect of war and the economy on the popular vote here, to a system of equations where we had one equation for each observation in our data set, and then turning that into a single matrix equation where we put the observations on the dependent variable into a vector, where we combined the independent variables into a single matrix where each column corresponded to one of the, well, one here corresponded to the constant and the others corresponded to the variables themselves. We have a vector of coefficients that are important in our theory. These are usually the things that our hypotheses that we're trying to test are about. And we're also mindful of the fact that in each of these 18 years, there's going to be some aspect of the popular vote that isn't explained by our model. So just kind of going through the different ways of representing the same basic idea as a system of linear equations with all numbers into matrices that represent those same numbers, and then kind of this nice pared down version of that same model where instead of having tons of subscripts and dots and lots of complexity to manage, we've just kind of got the overall structure here of dependent variables, a function of the independent variables times some parameters we're trying to figure out, plus a thing that we can't know. Okay, so that's, again, that is why we care about matrix multiplication. And you will find yourself getting more practice with that when you get to the regression class. In the next unit, there'll be a few lessons in the next unit that will also help you understand some of the particular matrix algebra that happens when we're trying to estimate those beta coefficients. So I'll see you then.